we'll get started. All right. So I think now we are going to start with dielectric conductor interfaces. So we are starting with the interface between a dielectric and an ideal conductor. Previously we had seen dielectric interface in detail for two polarizations, right. Now we are going to go ahead and see dielectric and ideal conductor interface, right. So the objective of this lecture is very similar to the objectives that we had for the prior lecture for dielectric. That is, we want to calculate the transmission and the reflection coefficients, all right, and we want to make some inferences, all right. Now I will draw the geometry that I want to consider, all right, first, and then I will make a few points and then we will proceed to the actual derivation. Okay. So in this case, the coordinate system that we pick is going to be identical to the case that we picked for the dielectric. So I am going to have the x-axis pointing up. Okay. Going to be having the z-axis going in the horizontal direction. This is the same coordinate system that we had used for dielectric interface. And if you want to form a right-handed triad, the y will be pointing out of the plane. Okay. All right. So here we want to be able to talk about dielectric on the left side, all right, and that is also going to be the medium from where the incident wave is going to go. Okay. So we are going to have a source at the dielectric medium. It is going to go and hit an interface, and it is an interface between a dielectric and an ideal conductor. All right. So conductivity is infinite. Okay. Sigma is going to be equal to infinite. Okay. So there are a few points to note. So first I will draw the incident wave and then we will start with the few points to note. Okay. So I am going to be having a wave going in the similar direction as what we had for the prior lectures. I am going to have it launched from here and it is going to go and hit the interface. This is the direction of your k. Once again, we know that we can formulate this problem in multiple ways depending upon the polarization configuration that you choose, all right. So we can start with perpendicular polarization because we have done perpendicular and parallel polarization before analytically for dielectric interface. We also wrote a program for perpendicular polarization, all right. So you may remember the terms much more than parallel polarization. I will begin with perpendicular polarization, right. So here that means that I am going to be having E field in the y direction, right. So I am going to mark that as EI. This means that the magnetic field is going to be pointing downwards. Okay. The other thing that we need to mark over here is the angle of incidence, which is theta I. All right. So there are a few points to make before we go to a full blown derivation of the coefficients. The first thing is the concept of ideal conductor means that no fields are going to exist inside of the conductor, right. In the electric case, you won't have a potential difference between two parts of the conductor, which means that you won't have any fields. Okay. So the job is actually pretty simple. Transmission coefficient need not be calculated at all, only the reflection coefficient has to be calculated. Okay. So we have to keep in mind that there is going to be absolutely no transmission for a semi-infinite medium of an ideal conductor. All you are going to get is reflection, right. So that makes the job a little bit simple, right. I draw a reflected ray. Okay. We will make some assumptions related to the polarization, all right, and one of the things that happens is you can make an assumption related to the E direction, H direction, etc. You can calculate the reflection coefficients. The reflection coefficient will be in line with what will happen physically. That means, in this case I am going to demonstrate what it means, alright. So, I am going to assume that the electric field direction does not change at all, right. So, I am going to say that let me assume the direction ER to be in line with EI, alright. It is an assumption, alright. If that were the case, the magnetic field would have flipped and it would be pointing like this. So, I will remove this word dielectric from here, that will give me some space to. Right. This is how it would look, alright. Now, what this means is, suppose I were to calculate the reflection coefficient, assuming that the direction of the reflected electric field is still pointing outwards, and I get a negative value, it will mean that the direction I have assumed is opposite to the direction as dictated by the physics, alright, the boundary conditions. So, what I can do is then I can look at whether the reflection coefficient is positive or negative. If the reflection coefficient is positive, the assumption is fine. If the reflection coefficient is negative, it means that compared to what direction I have assumed, I have to take a 180-degree flip, that is all. So, it really does not matter how you make an assumption, as long as your physics and boundary condition are going to be correct. Okay. So, here we are assuming that everything is going to be the same, and we will see at the end whether our assumed directions are correct or not. Okay. So, right now we do not know, we assume this. Angle of reflection is going to be equal to the angle of incidence, and in this case you have no transmitted wave at all. Okay. And we are talking about perpendicular polarization, and I will also mark that there are no fields inside of the conductor. So, this already gives us a hint that whatever happens, the reflection coefficient has to be unity. Okay. So, it already gives us, we already know that the electric field reflection coefficient has to be unity, alright, but we are just going to see whether the assumed direction is going to be the same or not, and also what are the total fields in steady state going to look like in medium 1. Suppose you are launching an electromagnetic wave, it goes and hits the interface, bounces back. We already know from our programs, right, that if it goes and hits a boundary and comes back, it will start interfering with the incident wave, the reflected wave and the incident wave will start interfering with each other. What do the total fields in medium number 1 look like? This is a question that we are going to answer. So, we will start with the formulation, alright, and the mathematical description of the electric field, alright. Looking at this diagram, it is identical to what we had drawn before, alright, for the dielectric interface. So, if I were to go back to my notes, alright, I have oblique incidence on dielectric interface. In this part, the description of the electric field is going to be identical, right. So, whatever I had derived for the incident electric field over here is going to be the same expression, because my coordinate system is same, direction of travel is same, all the variable names are the same, alright, which means that I just need to do EI naught e to the minus j k dot r, okay, and I would have got some expression for the description of the electric field, alright, and it looks like EI naught e to the minus j beta 1 x sin theta I plus z cos theta I. All I need to do is take the same thing, plug it in over there, because the expression for the incident field is going to be the same. So, I go back, okay. So, I write down my incident field, EI has a magnitude of EI naught, right, and the phase part is j beta 1 x sin theta I plus z cos theta I y hat. Okay. Okay, it is identical to what I had written before. The only thing now I am going to pay attention is to the magnetic field. Previously, I had just written magnetic field magnitudes, right. So, I had just written mod of H is going to be equal to mod of E divided by eta, but in this case I want to be a little bit more precise. I want to calculate what is Hx, I want to calculate what is Hz, and I will make a decision about their magnitudes once I have the full expressions, okay. Because when we wrote the program, we saw that electric field had a y component, and then we had Hx and Hz, we also plotted them, alright. We also found that the two of them were looking very different. Okay. So, it means that now we are in a position to look at it more closely, try to get the expressions for Hx and Hz separately, and then try to draw some more inferences as what is 0, what is not 0, what is a standing wave, what is not standing wave, etc. Okay. So, I think now I am going to write down the full vector expression for magnetic field also. So, I am going to write Hi is equal to, of course, the magnitude part is going to be divided by the intrinsic impedance of the electric field incident, right, multiplied by, I already know that the form of the expression from the perpendicular polarization, that it is going to look exactly like this, all right. So, if you go back to the notes and look at the form of the expression for the magnetic field, it would have been identical. Okay. So, I will still have e to the minus j beta 1 x sin theta I plus z cos theta I. Okay. The only thing that I want to be very specific about is, if I look at the diagram that we have drawn, the incident magnetic field is pointing downwards, okay, which means that I can project this on the vertical and the horizontal axis, right. So, I can take this to be a sum of two vectors, one pointing downwards and one pointing to the right. Okay. Right. And I can use trigonometry, I can say that theta I, so I can draw a line over here, I can say that alternate internal angles, this is theta I, this is 90 minus theta I, this is once again theta I. Okay. So, now I can say that this component over here is going to be my x component, and the horizontal component is going to be corresponding to the z component. Okay. And the reason why I want to pay more attention is because the boundary conditions are different for these different components, all right. So, in the previous case we did not have any free charges, so we just use tangential fields equal to 0, right. But here we have to be very, very careful when applying the boundary conditions, right. So, that is why I want to split them into two components and want to apply the correct boundary conditions, right. So, now I have the expression, the general form, and I want to split this into a x and a z component. I saw that the projection of the vector in the axis was going downwards. So, I will have minus x hat times some cos theta I, because it is pointing downwards. So, I will just say that the x component is going to look like minus cos theta I x hat, okay. And the z component was pointing in the direction of positive z axis, all right, and that value was sin theta I. So, I have plus sin theta I z hat. Okay. Okay. So, this completes the description for the incident fields. I do not have any transmitted fields, the only thing now I have to worry about is reflected fields. Okay. So, I will go ahead and write down the expression for reflected electric field. Let us say that we do not know much about it. So, we are just going to say that it has a magnitude of ER naught. Okay. Ultimately, you will get the reflection coefficient, etc. You can figure out what is ER naught with respect to EI naught. As of now, we are just using the same method that we used for the dielectric interface. Okay. Maybe that the reflection coefficient is equal to 1 and ER naught is equal to EI naught, maybe it is equal to minus 1 times, but we are going to figure that out. Okay. So, the general form is ER naught, all right, and e to the minus j beta 1, and the way we had written it for the perpendicular polarization was, it is still travelling along the positive x direction, but going in the negative z direction, all right. So, if you go back and look at the expression, we will be having x sin theta I minus z cos theta I. This corresponds to the k that you are going to be taking, right. So, the k value is going like this. So, you need to decompose k in two directions, then you will end up getting x sin theta I minus z cos theta I. Once again, the way I have drawn the diagram, I am assuming that this electric field is still pointing in the y direction, right. So, this is an assumption that I am making, but I can be corrected after I finish the entire derivation, right. So, the point is you can fix a problem, you can fix the directions in the way you feel you are comfortable. You can make the derivation. Once you finish the derivation, the transmission and the reflection coefficients will tell you whether the assumed directions are correct or not, that is all, right. Okay. So, I have the reflected field to have a y component and its expression is like this. Similarly, I can go ahead and write down the reflected magnetic field, which is ER naught divided by eta 1, all right, and I have minus e to the minus j beta 1 x sin theta I minus z cos theta I, which is the same form as the electric field, except that it has components. It has got a component in x, it has got a component in z, all right. So, we have to multiply this whole term just like we did for the incident field with the decomposition of your reflected magnetic field. So, now I have cos theta I x hat what's that? Okay. So, now I have the full expressions for incident and reflected fields. Now, I have to be applying some boundary conditions, all right. So, in order to, our objective is to find out the reflection coefficient and the directions of the reflected field with respect to the incident field, right. So, the convenient way is we have to take some position. So, the place where we will apply the boundary condition is z equal to 0. So, you can get rid of some terms in your math, all right, and then we can see what fields will add up, what fields will not add up, etc., right. So, the boundary conditions at z equal to 0. So, I will just say the you apply So, we apply boundary conditions at z equal to 0, tangential electric field, right. Okay. Tangential electric field, which is going to be say the sum of your incident is 0. Okay. Also note that the way we have assumed the direction of the electric field, entire electric field is tangential to the interface anyway, all right. So, I have just written EI plus ER, the tangential component is 0, but the way we have drawn, the entire value of the field is tangential. So, we could just take the sum and then equate it to 0. That would be a boundary condition at z equal to 0 as far as the electric field goes, right. For the magnetic field, the condition is different, all right, and we need to be a little careful, all right. We have a condition for the normal component of the magnetic fields, right. Okay. This will ensure that you do not have fields inside of the conductor. So, you have to either remember this or go back and try to derive this for an interface using Gauss's law, all right. But I think it is okay to remember this. H1 norm should go to 0. Okay. So, this is the reason that we split the electric field into x and z components, so that we can apply the boundary condition only to that particular component, all right. Now, let us have a look at what do these things mean. Do they mean something different or do they mean the same thing, all right. So, let us say that at z equal to 0, okay, I will have the incident plus the reflected fields tangential component is equal to 0, right, that is what I need to worry about. So, I substitute z equal to 0 for EI, z equal to substitute 0 for ER, and then I have to add them up together, right. So, I am going to say that at z equal to 0, I have ei naught e to the minus j beta 1 x sin theta I, okay, plus er naught e to the minus j beta 1, once again it will be x sin theta I. Yeah, so again it is x sin theta I, okay, because I just substituted z equal to 0. So, if you go back, if you look at the expressions, right. So, you will substitute z equal to 0, gets rid of this, only this part remains, okay, and same way for the incident electric field, only one part will, right, this part becomes 0 and this is what remains, okay. All right. Now, what do these mean? This means that the sum of these two is equal to 0, or I can say that rearranging this E r naught e to the minus j beta 1 x sin theta I is going to be equal to minus E I naught e to the minus j beta 1 x sin theta I. I have some common terms, right, can cancel them, and then this will give me the inference that E r naught is equal to minus E I naught. All right. So, even if you make an assumption about the electric fields in some direction, it does not matter as long as your derivation is going to be following that, all right, and as long as you apply the correct boundary conditions, you will end up with the correct value and the direction of the reflected field. I think in the prior derivations, some people had confusion why we had taken this direction to be flipped, the other direction is not flipped, etc. The reality is does not matter, all right, as long as you are consistent with the right hand rule for E, H and K, and as long as you apply the correct boundary conditions, it does not matter, your end result will tell you whether your assumption is correct or you need to reverse your assumption, that is all right. So, E r naught is equal to E I naught is the result I am having. This tells me two things. First of all, it tells me that the magnitude of the reflection coefficient, all right, the electric field reflection coefficient magnitude is equal to 1, and it also imparts a phase of 180 degrees to the reflected field with respect to the incident field. So, they are out of phase by 180 degrees. So, you can always say that this one at an angle of 180 degrees, or you could simply write this as minus 1, there is no harm in that also. Okay. Okay. Now, you can start drawing some analogy to transmission lines even here, all right. You can remember with respect to transmission lines, when we were dealing about Smith's chart, etc., we used to draw the short circuit on the left hand side of the impedance Smith chart, and the gamma plane was in such a way that gamma corresponding to short circuit was minus 1, and there it was voltage reflection coefficient, all right. So, in the transmission line, when you had voltage reflection coefficient to be minus 1, the condition that you were applying was a short circuit, right. So, you can say that this particular case is analogous to a short circuit in your transmission line. It is not the same, but it seems analogous to that, because you are just having electric field which is volts divided by meter, right. So, an analogy could be there, all right. So, it is also, if you have normal incidence, you will just have minus 1 and going back in the same direction, you can end up having standing waves with perfect standing wave ratio, right. Okay. So, there is some analogy even with transmission line, but it gets difficult simply because the angle of launch comes into the picture. In the case of transmission line, you never had the question of oblique incidence, it was always going hitting at normal incidence and coming back. Here you can always say that my theta I could be equal to 0, and that case will exactly boil down to a complete analogy with transmission lines. Okay. So, now let us look at the other boundary condition at z equal to 0. Okay. I had at h equal to 0, the normal components of the h has to be added up, and that has to be equal to 0. Right. So, I will be having E I naught divided by eta 1 sin theta I e to the minus j beta 1 x sin theta I plus ER naught by eta 1 sin theta I e to the minus j beta 1 x sin theta I. So, I have just taken the expression, substituted z equal to 0, and I am just writing the remaining terms that I am having over here, all right, and I am using only the normal component, okay. Normal component is only the z component in this case, okay. So, I am taking only the z component. But what does this mean? Does it give any useful information? I can quickly see that I can rearrange this, all right. So, I can rearrange this and write this down as ER naught divided by eta 1 sin theta I e to the minus j beta 1 x sin theta I is equal to minus EI naught by eta 1 sin theta I e to the minus j beta 1 x sin theta I. There are some common terms, all right. You can slash off the common terms. Once again, you end up getting the same information again, that the reflected field, all right. So, remember, in the previous dielectric interfaces, you needed two equations to solve for reflection and transmission coefficients, because there was transmitted and reflected field. In this case, you do not have a transmission coefficient at all. So, the two equations end up giving the same result, all right. So, once again, it is reinforced that ER naught is equal to minus EI naught. This means that if you are trying to solve some problems, you can always try to apply the boundary conditions only for the electric field, figure out the direction of the electric field, that is going to be good enough. Even if you apply the condition for the magnetic field normal, it means that effectively you are applying the same boundary condition again, you will end up getting the same result as reflection coefficient is equal to minus 1, right. So, having got this, right, one can ask a question as to what are the total fields in medium 1. Okay. Total fields in medium 1, suppose I write the field to be equal to EI plus ER. So, all I have to do is take the expressions, add them up together, that is all right. So, I am going to be having EI to be EI naught e to the minus j beta 1 x sin theta I, right, to the minus j beta 1 z cos theta I of okay. The way I have written it, it looks like it is in the power. So, I will just correct that. Just bring that down so that you do not have. Oh boy, simply cannot choose it. I think it's, yeah, okay. The minus sign is simply coming because ER is negative of EI, all right. So, it looks like e to the minus j beta 1 z cos theta I, again that minus sign will cause confusion. So, I will just put it here, right. So, it is e to the plus j beta 1 z cos theta I. So, all I have taken is taken the expressions, added them up together, and I have grouped the z terms together because I want to perform some trigonometric operations with them. I can use Euler's formula to say that the difference between the exponentials will give me a sinusoid. So, it will be 2j something, but because it is minus j beta 1 z cos theta I minus e to the plus j beta 1. So, it will be minus 2j sine theta I, all right, expression, right. So, I just wanted to get that with respect to z. So, that is why I have grouped them up together. Okay. So, I can just write this as minus 2j E I naught sine beta 1 z cos theta I e to the minus j beta 1 x sine theta I. And this is a huge expression, all right, and there is not much we can do to visualize this, all right. So, we will be quickly writing a program, okay. Whenever we have such a lengthy expression, because it has got cosine inside of a sine argument, all right, and then it has got product with exponential, it becomes tough. Even if you have got the expression, visualization becomes really tough when you have this kind of expression. So, we will be writing a program in Octave to just see what this means, all right, and then we will draw some inferences. As of now, this is an expression we have got, okay. Similarly, you can also write down, you know, the expressions for the magnetic field. So, you can always say that I have total fields to be equal to Hi plus Hr. There is a very lengthy expression, all right. I will just write it down, all right, and it involves grouping the z terms and applying Euler theorem to take the difference or the sum between the two exponentials in this case, okay. So, I will just write it down, then we will talk about it. This is the x component, and then I have a z component which looks like you can do this patiently by just adding the two terms and then applying some you know, grouping for grouping together the exponentials and trying to apply sum of the groups is equal to going to give you a cosine, and the difference between them is going to give you a sine. But this is a very big expression to form any picture in the mind, right. So, what we are going to do is quickly I am going to fire up Octave, all right. Whenever I have a large expression like this, I am going to fire up Octave, and then I am going to plug in some values. I am going to figure out what is known, what is unknown, and I am going to make some plots, okay. Then only we can figure out what exactly is going on. So, I will go ahead, open Octave, right, and I will write a small program just to visualize these expressions. Okay. So, I will start with okay. All I am going to do is I am going to start with what are the quantities that are fixed or known, all right. So, to understand this, we have to assume a fixed angle of incidence first. We have to say that let theta I be fixed, okay, and let us say that I will start with theta I that I consider to be easiest. Theta I equal to 0 will remove some of the terms, all right. It is easy for me to understand what is going on. So, I will start with theta I equal to 0, all the sinusoids will vanish, cosines will become 1, all right. So, my expression will look a little reduced, right, and I have x sin theta I, x cos theta I, all these things coming into the picture, and honestly I mean I could apply this at z equal to 0, but x could be anything. The boundary condition is applied at z equal to 0, x could be anything. So, conveniently I can choose x equal to 0, so that I reduce the expression even more, all right. So, if I had x sin theta I, now I know that it is 0. Okay. Then I just want to understand the dependence on z, because the incident field is going this way and then going back this way. There is some travel in the positive z direction and then going in the negative z direction. I would like to understand what is happening. Since I have assumed theta I to be equal to 0, it looks like the incident wave will go normal to the incidence, I mean the interface, and then it is going to travel back. So, I just want to plot the total fields as a function of this z in the dielectric, right. So, I am going to take some region, say -10 to 0, all right. 0 will be the interface, z equal to 0 is the interface, and we are going leftwards to some units of -10, okay, because only fields exist only there. On the right hand side we do not have any fields, we do not have to plot anything over there. So, z equal to 0 is the interface and you go backwards to all the way to -10, okay. Then I need to have a few more quantities. Incident electric field 1, okay, because it is easy to give 1 volt per meter and see what happens, whether it becomes -1, -2, etc., right. So, 1 volt per meter. Then there are other terms like beta coming into the picture, beta 1, 1, okay. And I think for the magnetic field case, you also need to know the characteristic impedance eta 1, 1. Okay. So, I fix as many quantities as possible to ones and zeros, so that I reduce my expression a lot, okay. Then I try to figure out what happens, then it is very easy for us to understand what exactly is going on. So, I have fixed everything to a very convenient number. Then I am just going to take the expression for the electric field. E1 is what we had written, all right. So, it was -2j, right, into EI, okay, this is EI okay, -2j EI naught sine of, okay, I need to look at the expression, sine beta 1 z cos theta I, right. So, okay, just typing it as it is, multiplied by some exponential minus j beta 1 x sine theta I. So, I will just move the j to the second because octave accepts like that, beta 1 x sine theta I. Okay. So, I have just taken the expression and plugged it in as it is. Okay. I want to start creating some plots. I will divide the screen into 4 because I have E, Hx, Hz, I need at least 3. I will just do them like this, one spot will be vacant, so that is fine, right. So, I will just make a subplot, 2 rows, 2 columns. The first plot that I want is of the electric field, right. So, I want to create a plot of position z, right, and then I want to plot, say, absolute value of E1. So, I want to see the magnitude of the E1 involving both the reflected and the incident field summed up together, total fields, okay. And I will also give a title to it because later on we will be having different plots. So, I am just saying absolute value of E, in this case it was EY, EY. Yeah. Also make this, say, just make it different plots of different styles or something, so that it is visible. Okay. Now, I am going to go ahead and run this. Okay. So, I am getting some plot, all right, and I will make the derivations or inferences once I have all the 3 components. Okay. But for now I see that there are a few things that I can quickly notice. First thing that I notice is with respect to the z direction, okay, I am having a standing wave pattern, all right, because the absolute values are going to 0 at some places which you will be calling as nodes, and the absolute values are going to 2. I supplied only 1 volt per meter normal incidence, the reflected one is adding up to the incident one, and the net field present in medium number 1 is 2 volts per meter. So, that is very clear, all right, and then it is going back and forth, right. So, I would like to, and another thing that I notice is at the interface, which is z equal to 0, my electric field is 0, all right. So, it is seems to be satisfying the boundary condition also. So, now I will go ahead, make similar plots for Hx and Hz. So, I will just say H1x, okay. I will have minus 2 times, okay, need to see the expression otherwise, Ei naught by eta 1. Cos theta I okay, it will be convenient to have the expression on the right side, I feel, to cos beta 1 z cos theta I. Into e to the minus j beta 1 x sin theta I. I think that part I am just going to copy and paste it from the line above because it is the same. Wow, that is a lengthy expression. I am also going to copy paste the plot comments. Okay. So, I have taken only the x hat component of the magnetic field and I have made it as H1x. While doing this, I will also finish H1z because I have to go back and forth between the two things. So, it is minus 2j Ei naught by eta 1. Okay, so, I will copy paste from the previous lines a little bit. So, this part is the same into, I think there is a sin theta I. Okay. Then I have sin beta 1 z cos theta I. I think the remaining form will be the same, there is no change there. Yeah. So, I will go ahead and make a plot out of this. So, I have just used BS, just means blue color line with square markers, all right. I don't think I have even specified a line. So, it is blue square markers. RD just means that red diamond is what I remember, all right, or I will make it red and upward triangle. So, that at least I know that it will work. So, it will just make some triangles for this plotting this particular graph. So, that 3 graphs look little difference. Yeah, K star just means black color star, all right. BS just means that blue color square, red color triangle pointing upwards, that is what it means. So, I just want to have 3 different plots, okay. I am just going to go ahead and run this, all right. Now, I think we can start to make some analysis, right. So, what did these expressions mean? At the boundary, the electric field is clearly 0, okay. throughout this region Hz is 0. Well, it is understandable because you had normal incidence. It did not have a component at all right. It had normal incidence, which means that your x was pointing in one way and the x was pointing in the other way, but it did not have a component in the z direction at all because your direction of propagation was plus z, and then when it is bouncing back its direction of propagation is minus z. So, magnetic field did not have a z component at all. So, it is 0 for theta I equal to 0 all right. The other thing that we notice is Hx all right is maximum at the interface. Ey is minimum at the interface. One can always calculate a Poynting vector right, and I can say that in this case I will take Ey all right crossed with Hx, okay, and I will get that the net power in x direction because I am having y cross z right, y cross x all right, I am having net power in z direction will be 0. Okay. So, in the z direction I do not have a power transfer all right, but what about in the other direction? So, I think we have to look at this more carefully. What does this magnetic field being equal to 0 even mean? Let us put some other angle right. Let us make the theta I to be equal to pi by 4 right. So, it is 45 degrees with respect to the normal at the interface, and then let us run this to get a little bit more idea all right. Now, I see that it makes a little bit more sense right. So, I am having Hz, Ey, Hx all of them to be non-zero. Once again I notice that at the interface electric field becomes 0, at the interface z component of the magnetic field is 0 all right, and at the same place the magnetic field x component is maximum all right. So, if I look at this graph, I have placed this graph one on top of the other deliberately so that I can see when Ey peaks Hz also peaks, when Ey goes to 0 Hz also goes to 0 all right. So, I can say that Ey and Hz are in phase, okay. Ey and Hz are in phase. Now, if I look at Hx, wherever E goes to minimum Hz goes to minimum, Hx has gone to maximum. Wherever there is a peak for Ey, there is a dip for Hx all right. So, I can say that Hx is in phase quadrature all right, or it is out of phase all right by 90 degrees okay, with respect to Ey or Hz okay. And when you have Ey crossed with Hx, since the electric and the magnetic fields are out of phase by 90 degrees, you do not have a power transfer in that direction. It is very similar to the case of having inductors and capacitors near circuits, where your voltage and current will be out of phase by 90 degrees. So, you will not have inductors and capacitor consuming any power. It is a similar case all right. So, I think now you have a tool. There are also other inferences one can make. At 45 degrees the peak value of the electric field that I will have in the in medium number 1 is still 2 volts per meter okay, and I am also having a magnetic field all right, which is 1 by which is square root of 2 times 1. So, it is 1.414 here, 1.414 here. So, there are some derivations that you can think about okay, but the critical part is when we have applied the boundary condition, the normal component of the electric field all right, the normal component has become 0, the tangential component has become maximum okay. So, this means that we need to think about this, the effects of this, and one of the things that we now need to talk about is surface currents okay. So, we need to talk about what kind of surface currents will exist in the surface of the conductor all right. So, summary is in the case of a dielectric conductor interface, in the dielectric medium you will be having standing wave patterns with respect to z, with respect to x it is a travelling wave. So, if you have a look at all the expressions that we have with respect to x, it is a travelling wave With respect to z, you just have a standing wave, right? Because at fixed values of z, you have some fixed values, whether it's a maximum, minimum, etc. is defined. But with respect to x, it's a traveling wave. Okay? And the other things that we have seen from the diagrams is that there is something going on with the tangential component of the magnetic fields in the case of a dielectric conductor interface, and we are going to talk about surface currents in the next class, right? So, I will stop here. Hope that now if you have lengthy expressions, one of the things that you can do is go back, open Octave, fix large number of quantities to zeros and ones, and try to write a simple program and see how to visualize these. At least this part you should be able to do. But if you do not do that, it is very tough to actually go back and draw with paper and pen, because you have to calculate so many things in the mind, right. So, this confidence you should have for all the perpendicular parallel polarization, you should be able to figure out what is fixed, what is varying, and then find out the unknown quantity confidently. Okay. So, we will meet in the next class. Right.